Right. So, the question I've got for you, this is a question I have for you. How do you eat an elephant?
One bite at a time.
That's quite right. One bite at a time. And that's what we're going to do today with this lesson. We're going to take one bite of each thing as we go. So we logically follow a route to get results at the end. For you, not for me, I can do this. All right. So let's have a look. So we're going to look during this lesson at interior manual lighting calculations. Now, many people say to me, with technology today and software, why do we need manual lighting calculations? What happens the day that you have no power? For whatever reason, load shedding or other, something we have been used to and we've kind of forgotten about it in recent times. But if load shedding got that bad that you had no power and you ran your computer battery and until there was no more power in the battery, how are you going to do a lighting calculation? You can't use the software, no computer. So, and this is something all students have a problem with. It's something that many other people have a problem with because they don't have the ability to do anything about it. But our students will have that ability. So, and the end result of this lesson is that you can tackle all the exercises in Module 7 with confidence. And we'll check to see, have we in fact managed to achieve that for you during the lesson? We'll just do some simple questions. All right. Nothing to worry about. So let's start. We're going to look at photometric data sheets. We're going to look at the Lumen method of doing calculations. And we are going to look at interpolation, which is part of the calculation, to find out what the coefficient of utilization is. We're going to then do the point method. It's a method of doing calculations for point devices. Downlighters, for example. You want to do downlighters in a toilet. They are point devices. It's a waste of time trying to do a Lumen method calculation for a downlighter, all right, in a toilet. So we'll teach you that. You'll learn how to scale plan drawings to an A4 PDF drawing, or vice versa. You have a A4 PDF drawing and you want to scale it to what the full-size drawing, a paper drawing would be. All right. And then we'll do a little bit of revision at the end. So in the first instance, before we go further, we need to understand what photometric data is. Now, let's have a look at one, and I'm going to share my screen with you to look at photometric data. And in a moment, you'll see that. Can you see that screen?
Yes, I can see it.
All right, you can see it. It's a little bit old, this photometric data, but still useful enough to learn from. It's a typical LED panel light. So typically the front page will usually have somebody's logo on it. It will have a photograph, and at the further down, it will tell you what it is, how much light it puts out. In this case, 100% light output ratio. If we thought about the old technologies like a fluorescent, the light went out in all directions in 360 degrees. All right. So some went up, some went sideways, and some went down. All right. Whereas an LED product, all the light is directed, in this instance, downwards. You do get somewhere a portion of the light goes up, so you call it a direct or indirect light, and the rest goes down. All right. But this, in this instance, all the light, when this thing's installed up there in the ceiling, all the light will be directed down. So it tells you that, it tells you what the wattage is, and it will tell you what the SHR stands for, a surface to mounting height ratio. All right. So a surface to mounting height ratio, it tells you something about the spacing, what the kind of spacing should be from the side and from lengthways. This bottom portion tells you everything about the instrument that measured the light, the photogoniometer in the laboratory, and it will tell you the range, all this information, and that will appear at the bottom of every page of a photometric data report. So that we know that it's constant and we're looking at the right data. So let's go and look at the second page, which is quite an important page. On the second page, you will see it will tell you what it is, what the weight is, what kind of diffuser it has, etc., etc. But more importantly, it will tell you it's a 40 watt, it runs on 230 volts, alternating current. The nominal flux, in other words, lumens that it produces, is 3,136. There's just one lamp with one set of LED, the test voltage, and then it will tell you the intensity maximum in candelas, not in lumens, candelas. And that will tell you it's 1,074 candelas. But if we want to see what the light output ratio is, it's 100% coming out of the light. All right. And the CRE class, it's direct. Light comes directly out of the light. And it will say the amount of light going up is 0, the amount of light coming down is 100%. And then on this side, it gives you surface to mounting height ratio, all right, in the different angles that you're looking at. So one lot of angles is length and the other is sideways. And then CIPC is the Chartered Institute of Building Service Engineers, right? It's an international body, and they give you surface to mounting height ratios as well. So they are nominal, all right? So if we go further down, we have a thing called the polar chart. This, can you see my pointer?
No.
Perhaps I've got to do it again. Okay. But there's this thing that looks like a clock dial.
Yes.
Right? That's called a polar chart. And you'll see on the polar chart, there's a blue outline.
Yes.
So there are two ways that you look at it. The one is if you're on top in the ceiling, looking down through the light fitting, you'll see that the light goes out and provides a certain amount of light on the desktop, for example. And the other way is looking through the light, and you'll see that it comes out in a beam. It's almost like a big teardrop. All right?
Mm-hmm.
And on the right-hand side, you'll see there's another chart which shows you the amount of light that comes out at different points. All right? It's in different colors, but it will tell you how many lumens it is. And the further away distance that it gets from the light source, the less lumens it actually produces, right? Right, steradians per meter. Okay. So we go on to the next one that counts, which is page 4 of 15 pages, which is the coefficient of utilization chart, where it gives you your room cavity ratio that you calculate here. I just want to familiarize yourself with the chart. And then you have various different columns here, and they depend on the reflectances in the room. So the reflectances that you have is 80% comes off the ceiling, 50% off the walls, and 20% off the floor. Or it could be 80%, 50%, 20%.
Hold on, can I just ask a question?
Yes.
Okay, so the first one, which is the ceiling, is 80%.
Yes.
And then in the wall, you've got 50, 30, and 10.
Yeah,
That's
you'll
the
only
first
have one of
column.
them. So it will depend on that particular calculation you're doing. It could be 80, 50, 20, all right? In
Yes.
which case you'd use the first column. You
Yes.
see there are 3 columns under that,
Yes.
all right? You'd use the column on the left-hand column. If it was 80 and the reflectance of the walls was only 30%, then you would use this middle column. And if the reflectance of the walls was only 10%, which might be typically of wood paneling or a black wall or a
Yes.
dark brown wall, it would be then 80%, 10%, and 20%, which would be the right-hand column. And then
Okay.
as you move towards the right, you'll see the combinations are different. And what is changing is the ceiling. 70%, 80%, at least 50%, 30%, and 10%. But you still have the options for the walls. And you'll see the floor is always 20%.
Yes.
Okay. So don't worry any further about that. For now, we're going to do that when we do the calculation. All right. I want to
Okay.
familiarize you with the photometric data, the data that you will use. Then we're going to jump all the way to page 9. And we're going to talk about this lovely cone diagram. It's often referred to as a cone diagram because it looks like an ice cream cone upside down. All right? But it's also known as the AAI figure. That's the proper name for it. All right. So when you look at this, all this top data is the same, and all the data at the bottom is about the instrument is the same. So we only worry about what's in the middle. And you'll see here it says that the flux out, in other words, the light out, once it's outside of the light fitting, is 2,289 lumens. All right. And here you have this beautiful cone. Now we talk about the Imax intensity maximum, which is located in the center directly at the bottom of the cone. All right? So we always calculate it directly under the light source. That, in other words, the middle of the cone. Okay, in the middle of the cone. Now you've got certain figures on this cone diagram. And if you look at the figures above the line are imperial. They're in foot candles and feet. And the figures below the line are in lux and meters, or in this particular case, centimeters. All right. So as you get further away, you'll get less lux and a bigger footprint. It'll light a bigger area. Okay? And that's why the cone. So at the bottom of the cone, it lights a bigger area, but it's got less light. All right? So just think about it with a torch. If you shine a torch, you'll see as far as the beam will go. But when you want to look further away, the beam doesn't get there. All right? It's exactly the same, because that is working on the same principle that you're going to learn in a moment. All right? Okay, so those are the 3 pages in this 15-page document that we work with in manual calculations. All right. So I'm going to end the sharing now. Go back to the presentation. And I just want to go and quickly sort out this pointer. Draw, and I just want to change the color. So it's there. Okay. Right. So let's move on to the next page. And we're going to talk about the Lumen method. Right. So there's certain things that you have to remember with the Lumen method. Very simply, it only calculates horizontal illuminance. Right? Horizontal. In other words, from the light fitting up there onto my desk, the desk is horizontal. Okay? If I wanted to see how much that light's going to put on my face, I need to have vertical illumination. How much vertical illumination would there be? But the Lumen method doesn't calculate vertical. Okay? You understand that?
Okay.
It calculates maintained illuminance and not initial illuminance. Now, initial illuminance is not that it doesn't really apply to LED, but if you took fluorescent and you turned fluorescent on for the first time, the initial luminance would be higher until it settled down, and then it starts to fall. And over the lifetime, it depreciates. It gets less and less and less until the light goes pinkish color and is no longer actually making light. The old fluorescence, all right.
Yes.
But there are also some limitations about when we can use the Lumen method. And we need to always remember this. You can only use the Lumen method,
Sorry.
bless you,
Sorry.
for the interior. You can't use the Lumen method outside. It's based on the 3-surface model: ceiling, walls, floor. In other words, a box. All right? There have to be ceiling, walls, and floor. The room surfaces are diffuse. Now, you remember you learnt about specular and diffuse. Specular was typically like on an early morning, and you look across a piece of water and it's like smooth, and you get a perfect reflection of the mountains and the trees in the water. That's specular. But it's diffuse because the wall surface is not perfect. So you get imperfections. So the light will reflect off in different directions. The luminaires are always evenly spaced. They're evenly spaced along its length and they're evenly spaced from each other across the room. Okay?
Okay.
You can only use one type of luminaire in a calculation. You can't have a lot of different luminaires. You can do that in software, but you can't do that in manual calculations. The room is always empty. There's no furniture or equipment. Okay? It's always empty. And then here's something very important, that the length to width ratio may not exceed 1.6 to 1. We'll do a couple of exercises. That's why I asked you the question. What happens if it's more? And I'll tell you how we do that. And of course, I said to you, the illuminance is maintained. So it'll be across the surface. It's the same maintained light.
Okay.
Which, if we were using software, is not the way we want to design. But we don't have an option with the Lumen method. Okay, so let's just go over some points here. Here we have a room, and there's certain technical definitions that we need to understand. There's our box. We've got the ceiling. We've got, can you see my pointer now?
Yes.
We've got the ceiling, we've got the walls, and we've got the floor. All right. If we measured the light on the floor, our floor cavity would be, what would the value be? It would be 0. But the normal thing that we do is we always measure the working plane. And the working plane is usually 0.75 meter. Okay?
Okay.
So what would our floor cavity be? Our floor cavity height would be 0.75 of a meter. All right?
Okay.
Now, on the ceiling, there are other things we need to work out. What is the ceiling cavity? If we used an LED panel, where would we mount the panel? It would
On
be
the ceiling.
mounted in the ceiling.
Yeah, in the ceiling.
All right? So we would have a ceiling cavity of 0.
Yes.
All right? There would be no ceiling cavity. But if we had a surface mounted fitting, and the fitting was mounted there on the surface, how would we calculate the ceiling cavity? If that fitting was 7 centimeters in size, then our ceiling cavity would be 7 centimeters.
Okay.
All right? Because we measure the ceiling cavity, that's where the light comes out. So we're only interested where the light comes out. So therefore, the ceiling cavity, where there's no light, would be 7 centimeters.
Okay.
But if we are using a suspended fitting, or a high bay for that matter, we measure through the fitting where the light will be emitted. See the dotted line? We measure through there. So our ceiling cavity then is from the ceiling to that dotted line. So we'd calculate what that is.
How?
Now we're
The
going to do an
length.
exercise on it. We're going to look at the calculation sheet in a moment. All right? So what we're interested in is calculating what the room cavity ratio is. In other words, the space between the working plane and the light fitting, wherever
So
it
can I
may be.
ask, can I ask a question?
Yes.
So, um, so let's say this is an office.
Yes.
What happens if it was a factory with regards to the floor cavity?
Well, it would depend on what we normally will, in this method, we'll always use 0.75.
Okay.
All right.
Okay,
Because
even
the
if it's a
room,
factory.
remember, the factory's empty. The calculation, remember what I said? If we go back, there's no furniture or equipment.
The reason why I'm asking is because generally in an office you've got a desk, but in a factory you don't necessarily have a desk,
Yes.
if you know what I'm saying.
But in most cases, you've got machines, and the machine's height could vary. You
Yes.
might have a chap standing working on a lathe.
Okay.
So
So it would
the,
also be
the lathe
0.7.
height is going to be higher than a desk,
Yes.
right? But you might
Yes.
have somebody working on a machine at desk height.
Okay.
But those things we don't know
Yes.
because it's empty. All right. So we
Okay.
use a safe calculation is standard 0.75.
Okay.
All right. If we were using software, it would be a completely different ball game. Because there we can, in a space, in a factory, we can have one machine at this height, another one at that height, and the software can do the calculations at different heights
Okay.
in different places. Right. And you need more light on the machine than you do in the walkway. All right. So it's a very different environment. But when you're using software, but we're not using software here, we're doing manual calculations. Okay.
Okay.
So do you understand that now? Ceiling cavity, which will depend on recessed, surface mounted, suspended. Okay.
Yes.
And floor cavity is between the floor and the working plane. All right. And typical working plane is 0.75.
Yes.
Right. So the room cavity is going to be the total room, floor to ceiling, less the ceiling cavity. Right. So it'll be floor to ceiling height minus that cavity and minus the floor cavity. And what's left is the room cavity ratio.
Okay.
All right. But we're going to do that in a moment. So now let's apply the Lumen method. We apply the Lumen method. So we have to go through the following steps. These are the steps we must take. You select the space. You measure it. You measure the length, the width, and the height. 3 things that we've got to know. Then you define the working plane. All right? You could have another working plane, just by the way. But if you don't know another working plane, you use 0.75. Define the room cavities. And that's easy. Because if you know what the working plane is, it's easy. Then we've got our floor cavity. If we know what light fittings we're going to be using, because we've made our selection, it says here, select a particular luminaire type. So we select it, then we're able to calculate what our ceiling cavity is. And once we know all of those, we're then able to calculate what the room cavity ratio is. And after that, we can calculate the coefficient of utilization. And then the next step we're going to do is we calculate the light loss factors. Then we work out one of two formulas to work out the number of luminaires, or whether the number we've got will produce the right amount of light on the working plane. And then we've got the number of luminaires to give the desired result. So let's look a little bit closer to this. So let's go and get I'm going to share my screen again. Just positioning it right first. All right, it'll take a second. As soon as you can see it, you tell me.
I can see it.
You can see it. All right.
Yes.
Perhaps I want to make it a bit bigger. Not quite so big. All right. So essentially, you complete everything in the yellow on these forms. Okay? And you put the project name, the luminaire that you've selected, the lamp type and model, the light output that it puts in there, how many lamps, what the light output ratio is. These are just nominal figures I've put in here, just for the exercise. And they're not real, right?
Okay.
They're just examples. And the total luminaire, initial lumens per luminaire, 4125. And I said that the ceiling's 30, the ceiling should be 80%, sorry. I can't change it whilst I'm working on it. 30%, 80% for the walls, and 20% for the floors. Don't worry whether they're right or wrong. Okay? It's the example. Then we go and we say, what's our floor cavity height? We put our working plane in there. The floor cavity height is the working plane. All right? And we take the room height, which is 3.5 meters, less the 0.75, gives you 2.75. All right? So that's our room cavity height. So now we go down here and we'll see that the room is 27.5 meters by 20 meters, which is 550 square meters. Okay? This is just a matter of filling things in the yellow. Okay? And we multiply that by that and it will give us 550 square meters. Happy?
Yes.
So then we go and we do our calculation, which is 5, a factor of 5, times the room cavity height. The room cavity height, 2.75, times by the length plus the width. So when you do that calculation, how do you do a calculation that's got different types of calculations within it?
BODMAS.
BODMAS, there we go. So the first thing you're going to do is you're going to calculate what the length plus the width is in there, so that you can then do the multiplication right the way through and divide it by the area of 550, which gives you 1.1875 as your room cavity ratio. All right?
So if I can just ask, so it would be the room cavity height, which was 2.75. So it's 2.75 times 5. Correct? And
Yeah,
then
5.
times your
It'll be
times
that
your
plus that. So that it's the length plus the width. So it's going to be
yeah.
47.5. It'll be 5 times 2.75 times 47.5. Length
Okay.
plus width
Yes.
divided by 550.
Okay, and then just on the mathematical side, so I mean you can do it on your scientific calculator, correct?
Yeah.
But I mean if I wasn't doing it on a calculator, I would obviously do my brackets first, which would be my length plus my width, and
Yes.
then I would say the room cavity height times 5, and then I would times both of those together,
By
and
the
then I would divide by the
47.5
area.
and divide by 550.
Yeah.
Correct.
Okay.
All right. Now we've got to go and we do that calculation, but I'm not going to even talk about it now because that's a
Okay.
set exercise I'm going to teach you. All right.
Okay.
So we do an exercise, it comes out, there we get our coefficient of utilization, and now we have to enter the light loss factors. Now, if you read the manual, there's a whole load of light loss factors, but there are 4 very important ones. All right, and they are here. So the first one is the ballast factor. Now, is there ballast in an LED?
No.
No. But you can't put a 0
Okay.
because if you multiply these 3 by each other times 0, what is your answer going to be?
0.
That's right. It's going to be 0. And that's why we always put a 1 in there. If it's LED,
Okay.
we put a 1. Right. And then you put the actual factors here, and you get those from different tables.
Where?
All right. And we're going to look at those tables to say
Okay.
where we get these from. And the
Okay.
room surface dirt depreciation, you also get it from tables. And once you've put those values in there, you will then multiply them again with each other until you get to the total light loss factor, which will
Okay.
be there. Okay? And you get that by saying 1 times 0.96 times 0.96 times 0.5 gives you 0, whatever it is. Okay. Then we have to go on and we want to calculate how many light fittings do we need. And in this particular case, you're told you have to provide 300 lux. So you take the 300 lux multiplied by the area of the room, the 550, divided by the lumens per luminaire, which is 3,136, all right, multiplied by that coefficient of utilization, which was 0.78 in this example, multiplied by the light loss factor, which was 0.4608, and you will get a certain value of luminaires. All right? Okay. It's pretty straightforward. But now you want to check, is my calculation correct? So now you go back and you say, well, okay, I've worked it out to be 111 luminaires. So I put the number of luminaires in there. So I say here, 111 luminaires times by the 3,136 lumens that we got from the photometric data, multiplied by the 0.78 in this example, the coefficient of utilization, multiplied by the 0.46, whatever it is, for light loss factors, divided by the area of the room, the 550, and that will tell you that you're going to get 299 lux, which is good enough. 1 lux short of 300. Okay. So, yep, that's fine. If I want to really make sure I've got that, maybe we need, because we've always got to have our spacing between luminaires and across the room, across the width, it's got to be even spacing. So it's very seldom we'll end up with an odd number. So perhaps 112 luminaires to be safe.
Okay.
We decide that. It's a sort of just a rational thought.
Yeah.
Okay. Right. So that's the form. That's the form of it. So I've ended the sharing. So let's go back to the presentation. Okay. But in the process, let's look at certain factors. And I'm going to share my screen again. Give it a moment. Can you tell me when you can see it?
I can see it.
Okay. Now this particular form, and you have a copy of that because it's in the folder, all right?
Yes, got it.
This form was developed by a student, a graduate, many years ago. Excuse me. The student was from Gaborone in Botswana. And Clive developed this. Now this section, the big section, can you see my pointer?
No.
No, okay. The big section to the right of the little table with figures in it, the big section in words is a description of the place. And it's very dirty, or it's dirty, moderately dirty, clean, or very clean. Those are the categories. And it will tell you under each of these things what that place is like. So you can determine then what are the factors going to be that I'm going to use. In this particular case, we're looking at the light exposure, so the luminaire dirt depreciation factor. How much dirt is going to accumulate on the light fittings in this place if it's very dirty? Or on the other extreme, if it's very clean? Because that's going to guide you to how often you have to do maintenance. Get up there, clean off the light fittings to remove the dirt. Why? Because if dirt continues to accumulate on the light fitting, it's going to take light away. So you're going to have less light on the desk, for example. And the more it gets dirty, you get less and less light. Okay? So if you get less light, then it won't comply with standards anymore. So we plan to get up there and clean light fittings. All right? And you can go and you look at the columns here, and you'll see that on this side, it tells you how many years. And you'll set it according to whether it's clean or very clean. And the columns are all there, matching these descriptive columns. So you can work it out to see. When it gets to a certain point, you'll see, well, I'm going to be losing too much light. Okay. So for your luminaire, your dirt depreciation, luminaire dirt depreciation table, you use this table. All right?
Mm-hmm.
Do you understand it?
I do understand it. I just wanted to see how it's okay. But we don't need to put this factor in any. Oh, we do, the LDD.
That's right.
Yes. But
LDD.
now explain to me, so how do we, because I mean, which number do we put in? Because we've got 0.5 years, 1, 1.5, 2, 2.5, 3. So how do you know which?
Okay. You wanted least depreciation. Okay. So you're going to look at that table. I've got to squint at it because it's small, and I don't want to increase the size now. Let me do it there so I can increase it. So we're going to
There we
look.
go.
Typically, in general, we plan to clean every 2 or 3 years.
Okay.
But that will be dictated to by the space. Is the space dirty, very dirty, moderate, clean, or very clean? It's very.
Okay.
You've got a very clean office. It's a new office. It's effective air conditioning. There's not a lot of dust accumulation. The office is cleaned regularly, and so on. Then you're probably looking at about 3 years. So if you go to 3 years and it's very clean, you're running at 0.946. You've got very little depreciation there. So you clean it just because it's good practice.
Okay, but what about
Contrast,
like?
it's very dirty.
Mhm.
All right. If it was very dirty, that's 0.550. That means that you're losing a lot of light because it's very dirty. So you need to clean. So if you don't want to lose too much light, you might clean every 2 years or once a year even. Okay?
Okay.
But very often you've got to look at the cost, how cost relates to it. I'm telling you now practically. Because if you're doing in a factory, which is very dirty, you've got to get cherry pickers.
Mm.
Get up there to get to the lights to clean them and so on.
Mm-hmm.
So there's a whole lot of factors. The rental of a cherry picker, how long is it going to take? With you've got to, when can I do it that there isn't disruption to the production? So I've got to do it at night time. So the staff doing it have to get overtime, etc., etc. All right.
Okay. So when we have an example, so the okay, because I see in the manual the problems you've actually noted the LLD. No, you
Yes.
haven't noted that. Yes, you've actually noted it there.
Yes.
Yes. Okay.
All right.
All right. Okay.
Okay. So let's stop sharing that one. Okay. Let's look at another chart. We also use the same chart to calculate what the room surface dirt depreciation is.
Oh.
Right? So we can use this for both, for the room surface dirt depreciation. So how much dirt is going to accumulate on the walls, on the floor, or on the ceiling for that matter? Because remember, hot air rises. So very often it will take the dirt up with it onto the ceiling and deposit it on the light fittings as well as the ceiling. So what about that cleaning? Okay. So those are the factors you could. Lamp lumen depreciation was more applicable to the old technologies. Mercury vapor, high pressure sodium, fluorescent, and so on. LED has depreciation over a long time. So if you say LED is good for 15 years, for example, it will start depreciating at that point in time, just close to it at that end. But for most of its life, it hasn't depreciated at all. Not
Okay.
like old technologies, all right?
Mm.
So that's why generally you'll say lamp lumen depreciation, we put it in at about 0.96. All right. So that's the normal figure that we use for it, for LED. Okay.
Okay. And for fluorescent?
No, fluorescent, you've got to work out what the age is, and then you work what that is. And you'll see lamp lumen depreciation. The manufacturer calculates it to about 40% of life. So what's the life of a fluorescent tube? Average life of fluorescent tube is round about anywhere between 6,000 and 8,000 hours. All right? When it starts depreciating, it will depreciate within that time. So, and we get really worried when it gets 40% of life. Because once it starts depreciating to a certain point, you haven't got enough light for the people to do their work. Right? So you've got to replace them or whatever the case is. And as you know, I think it's towards the end of next year, there's no fluorescence. Can't sell them for new. You can only sell it for replacements.
Fluorescent tubes.
Yeah. All right. So we go back to the presentation. So we've done the worksheet. Now let's look at interpolation. All right. This is to calculate the coefficient of utilization. Now, don't worry your head too much about this one. This is academically and mathematically correct. And you know that anything on the right-hand side of the equal sign, if we take it to the left-hand side, the sign within the calculation has to change. So
I learned that recently. I learned that recently.
Yeah.
I didn't know
Don't
that.
worry about it. Don't worry about it. But the important thing is to see, here's the calculation, it's all done, and this is in the manual, and it comes to 0.841, all right? So there it is. But let me teach you my method.
Okay.
My method. You will not go wrong with it.
Okay.
Okay. When you go and look at your tables, in the table, you have to determine whether the value that you want is closer to the higher number or the lower number. Right? So if your coefficient, at least your room cavity ratio, is between 1 and 2, you ask yourself the question, is it closer to 1 or closer to 2? In the case of it being closer to 1, you have to take away from that the value of 1. So if we look at our table, we'll see the value that we're going to work with, because the values we've got for 1 is 0.94 and for 2 is 0.79. Okay? 1 and 2. And we say 1.34 is closer to 1. So therefore we've got to take away from 1. So we go and we say 1 is 0.94. There it is. And we've got to take away. Okay? And now we want to find what the reverse is of this 1.34 the room cavity ratio that we calculated. Okay? So we want to know what's the opposite side of it. In other words, the reciprocal value. So we take 2 minus the 1.34 to calculate that value. So we can't take 1.34 minus 2 because we're going to get some weird number and it'll be a minus number. We can't work in that. So we use 2 minus the 1.34. Then in the next brackets, remembering BODMAS, 0.94 minus 0.79. Those are in the tables. We got that from the table. Right. So now let's go to the next line. We've still got the 0.94 minus, calculate that part out, 0.66. Calculate that out, 0.15. We move to the next line. It's still the 0.94 all the way, minus that multiplied by that gives you 0.099. 0.94 minus that amount gives us a coefficient of utilization of 0.841.
That looks,
0.841.
yeah, that looks very easy. Can I take a screenshot of that calculation?
You're going to get this recording anyway.
Okay.
Right? But you can
Right.
take a screenshot.
Thank you. That does look a bit, your method looks good. Got it.
It works
Thanks.
every time. All right.
Okay.
You don't have to worry about changing the signs
Oh,
and all those funny things.
okay.
All right.
Okay.
There it is. Right, let's move on. It's simple. You got it? You say, what's my target
Yes.
value? If I look at those two values, 0.94 and 0.79, is the 1.34 closer to 0.94 or 0.79? No, it's closer to 0.94. Therefore, it must be a minus sign. Let's say
Because
it was 1.64. All right? Then it would be closer to the 2. So this sign would be, the value that we'd put in here is 0.79. All right? The lower value, which is equal to 2, plus, and then these things would be the same. This would be 2 minus 0.64.
Sorry, Phil, can you just say, isn't it normally always minus?
No.
But can you explain the why it's a minus and why it's a plus just one more time?
Right. Let's say that we've got a figure of 1.64 is our
RCR value.
RCR value.
Yeah.
Okay. So now there's the value of 1 and there's the value of 2. Is 1.64 closer to 1 or to 2?
To 2.
Okay. So we would start off here. This would be 0.79.
Yes.
Plus, because the RCR is not this equal to 0.79. It's 0.79, but you've got to go up towards 1.
Okay.
You follow that? Okay.
Yeah.
You can't take it away from there because then it'd be going towards 3. Okay. So it becomes plus. And then the rest of the calculation stays the same, except this figure changes to 1.64. So that figure will be different. That will be the same. And this will all just be 0.79 plus. and whatever this result is here.
And in this situation, your RCR is 1.34.
Therefore, it's minus, because 1.34 is closer to 1 than it is to 2.
Okay.
Right.
Okay.
If it was 1.5, you could do either or. 0.94
Okay.
minus or 0.79 plus, because the answer will be the same.
Okay.
All right. Okay. But this is a humdinger. It works every time, but it is not academically correct to teach this, and it's
Okay.
mathematically correct to teach this. All right, strictly mathematical. Strictly mathematical and academically correct is this method.
Okay.
All right. But if somebody's battling with that method, changing the sign every time you move it across to the left-hand side, right? And people become frustrated and they make mistakes in the process.
Mm.
And then their answer's wrong. And they do their exercise in the assignment and they get it wrong. They can't understand why. That's why. If you're haven't done maths and you're not good at it, let's give you other tools to do it. And this is the way to do it. Okay.
Okay.
It works I don't use that other method. I use this if I have to do the calculations. All right.
All right.
Let's move on.
With you.
We're going to now do the point method. When do you use the point method? You use the point method if you've got a point device, a downlighter. All right. Or there's a fitting used in an exercise in the final set of exercises for module 7. And we're going to deal with that shortly, which is an exterior exercise. Right? And how do we calculate it? So in the point method, there are 3 basic calculations. The first one is the basic method. There's a variant point method, and there's a point method in certain outdoor applications. Okay, there they are. And we're going to tackle those. So what we have to understand with the point method is what's it based on? It is based on the inverse square law. Right? It's a law in mathematics and in science, which is the inverse square law. It's in lighting, we use it in this way, but it's also used in for other calculations, the inverse square law. And very simply, it uses E for illuminance. All right. E always means, in lighting calculations, illuminance. So if you see E, you know you're going to have to calculate what the light's going to be on the surface. Okay? And that's equal to intensity, the strength of the light, intensity, strength of the light, divided by distance squared. So distance, if we say the distance is 1 meter, 1 times 1 is still 1. Okay? So the distance squared, and we calculate the light, which will be directly under the center of the luminaire. So here's this lamp, for example, and the center of the lamp is there. So there is your center line. So at 1 meter away from that lamp, in this example, you would see that your illuminance is equal to the intensity divided by distance squared. So at 1 meter away, the area covered would be equal to one of these blocks. All right. I've not seen a light that produces a block size, but just this is for understanding. All right.
Mm-hmm.
But if we move another meter further away, that same light diminishes in brightness. The intensity is the same. It's the same light, same intensity, but the amount of light falling is equal to 4 blocks. So in other words, it's 1/4 of the strength that it had at 1 meter. All right. And if we go at 3 meters, just 1 more meter away, it becomes 1/4 of what it is there. And it lights up 9 blocks. All right. So that's the inverse square law. And I said it to you earlier when we were looking at the cone diagram. Do you remember? If you go and you study the cone diagram, you'll see the further away you get, the same light is giving you a bigger area that it's lighting up, but the lux level is much less. All right? So if we always remember that, so the higher it is from the area we want to light, if we want to achieve a certain value, we're going to have to use a brighter light to make that value because of this thing, the inverse square law. Okay. So let's move on. So if we want to calculate the light that falls on the desk directly under the light source, this is the basic inverse square law, directly under the luminaire, we use this formula, E, the illuminance, there's where the illuminance is, okay, is equal to the intensity, which comes out of the light, divided by distance squared. That distance from the light to where we want the light. Okay? That's the formula. Easy. It's an easy formula. Okay? Once you've got it, you never forget it. So it's one of those things you remember. You remember. Put it in your mind map.
Yes.
Okay? The next thing, because we're using point method, we also have to know something about
Hypotenuse.
this thing. It's the Pythagoras theorem. Right? Pythagoras' theorem. And in Pythagoras' theorem, c squared is equal to a squared plus b squared. All right?
Mm-hmm.
So if we take this, that squared plus that squared will be equal to c squared.
Mm-hmm.
That's Pythagoras' theorem.
Okay.
And in this particular one, it's a right angle triangle. All right? What is a right angle? How many degrees in a right angle?
90.
90. So it's a right angle triangle that we're working with. But in total, how many angles are there?
3.
3. So if I said to you this one here was 30, what will that angle be?
Which one?
This one here.
If that was 30.
And that one's 90. How much is that one?
This one's 30 and this one's 90.
Yes. So what's that one going to be?
60.
That's right.
No. Okay.
60. It's quite right. because 3 angles together make 180 degrees.
Yes.
Always.
Yes.
Always. All right. For a right angle triangle. So that means there are some easy things to work out.
Yes.
So let's carry on. Now we want to look at the variants of the inverse square law. And there are a couple of variants. And when do we use them? First of all, the one is we want to work out if we know what it is in the center, right in the center of the light, the pool of light. Let's call it a pool of light. In the center, we know what that value is. We want to know what the value is at the edge of that pool of light. In other words, to the side. And the other one that we want to know is we have a light source. You know those bullnose downlighters that you get that you can turn them, they
Yes.
swivel, and we can point it towards a painting on the wall.
Mm.
Right? So we're shining it at the wall, and we want to calculate what the illuminance is on the painting. Right? So that's the other variant. Those are the two things. So we calculate 3 things with the point method. Directly under the light, to the edge of the beam of light on the working plane, and also on the wall if we shine the light on the wall, on a vertical surface. I just want a sip of water. So let's look at those. Here we've calculated under the light. Now we want to calculate at the edge of the light. So we use the inverse square law, E equals intensity divided by distance squared. So we do that part multiplied by cosine of the angle that we're talking about. So we would have that angle, for example, there. Okay. So that's the one. Cosine. E is equal to intensity times cosine of the angle divided by distance squared. All right. Let's look at the other one. Then I'll tell you how we get these things. This is the other variant. We want to shine the light onto this painting. And this CP, center beam candle power, right? Which is the same as intensity. Okay. So E is equal to intensity times sine of the angle. So we'd say, here's the angle. The angle would be here. Let me draw it in for you. There's the angle. Divided by distance squared. Okay, so this sounds really, really difficult, eh? But it's not. Let me share my screen with you. I'm just going to put that on there, over there, like that. Increase it. And let me share it. Tell me when you see it.
I see it.
Okay. So now, let's say that angle is 30 degrees. And we want you to calculate whether it's cosine or sine in either of those instances. So if we want to get the cosine, you'll see that this is a trigonometry table. Don't be frightened by the word trigonometry table. We'll say it's a convenient table. All right? Call it a convenient table. And there are three columns. There's a sine, S-I-N. There's cos, which is C-O-S. And there's tangent, which is T-A-N. But let's go and look. And we want to work out that beam at the edge of the distribution on the desk. And we say we want to look at 30 degrees. So we go down to 30 degrees. All right, can you see 30 degrees?
Yes.
Can you see it?
Yes.
Better?
Yep.
30 degrees, cosine, which is the middle table, and it would be 0.8660. So, therefore, we would go and we'd say E is equal to the intensity times that figure of 0.8660 divided by the distance squared. Right? And that would give us what the illuminance is at the edge of the beam. All right?
Okay. Yeah.
So it's just a simple little multiplication and division exercise at the end of the day.
Okay.
If we said that same beam angle was 30 degrees for the exercise, and we want to measure what it is on the painting, we wanted to do a calculation of E on the painting, and we go and look, we've got to use the sine. E is equal to intensity times sine of 30 degrees. Sine of 30 degrees would be 0.5000. All right? Divided by distance squared. Okay. Easy peasy. Easy peasy. So you combine this table, this convenience table, all right?
Yes.
Which is where you go and you look up your figures. If you were doing 60 degrees, you would
got
come
a similar table in the, this table over here.
It's in the manual. Yeah, it's there. It's the same table.
Oh, yeah, yours is just longer.
Yeah.
Okay. Oh, yeah. You've just condensed it on here.
Yes. Okay.
So, and then, yeah. Okay, got it. Yes.
All right. And if the angle was 60 degrees, we just swing over to the other table, the other page.
Yes.
Where it is on that one, and you look up 60 degrees, and you'd see in the 60 degrees, the cosine is 5. Okay. And the sine is 0.8660. It's just reversed. Did you see that?
No, show me again.
60 degrees
is
the reverse of what 30 degrees was on the other, in the other column.
Yes, I see.
You see?
I'm looking at my page.
It follows, it's logical. 30, 60. Yeah. They are related in some way. And that's how they're related. Okay. I'm going to end the sharing. So, armed with the convenience table, we're able to calculate these three versions. You've got the inverse square law, which you don't need the table for, but the inverse square law with the cosine or the sine. Sine is on a vertical surface that we want to calculate what it is. For example, you want to light up a rack in a retail store for the promotions at the end of the month, you would calculate what the light's going to be there using E is equal to intensity multiplied by sine divided by distance squared. All right?
You obviously know what your distance is.
Yeah, you either know what your distance is or you can calculate distance because you know what Pythagoras' theorem is. So if you know one distance or one of whether it's the hypotenuse, the opposite, or the
adjacent,
the adjacent, then you can calculate. So you just need one and the angles, and you can calculate the others. All right.
Yeah.
So let's move on. Okay. So now you can see this one, given information. Can you see it?
Yes.
All right. This is that exercise that you're going to come across in the last series of exercises in part 2. All right. In part 2, the assignment, there are 3 exercises. There are 2 quite simple ones, and then you get this last one, which is a bit of a challenge. But I'm going to help you through it so you'll be able to understand this one. So, a luminaire to use throughout is this particular one. It's a floodlight, but they use it in the canopy of a petrol station. All right, shining down onto the driveway. There it is. It's 92 watts. It's got a 62 degrees beam angle, a 60-degree beam angle rather. You're given a forecourt layout, which we're going to look at. It's a double-skinned canopy. Therefore, we're able to recess the luminaire. It's not surface mounted, but recessed.
No, I'm here with you.
There's the canopy size. And it's the mounting height is from the driveway to the luminaires, which is the underside of the canopy, is 4.5 meters. The pump island curb height, the pumps are all mounted on a little island, which is raised off the driveway. Mm-hmm. And the step from the driveway to the top of that little island is 100 millimeters. Okay, 100 millimeters. And there are 4 pump islands, each with 2 pumps. Okay, that's the narrative. So, what we need, we've got to have 300 lux minimum on the driveway, and we must have a minimum of 150 lux on the pump face. In other words, the place that we see it's so much per liter, and when we filled the car up, it came to 1,000, whatever it is. Up your SUV, or to fill up my Honda CRV. All right, it's about the same. Okay, so there we've got, this is just information that we need to do a calculation. So there we have our little sketch of the layout. Now this is the same sketch we were given when we did this job. Still, it was a job that Peter Willig and I flew to Durban for, and this is down on the south coast, and this is the petrol station. And this is the diagram that I was given. Okay, and these are the dimensions that are physically measured off. Okay, and there they are. So, what we don't know how many luminaires we're going to need. We don't know what the height of the pump is from the base of the island after the curb height of 100 millimeters. I knew what it was because I measured it, all right? But that's part of the problem that you have to calculate. So the easiest thing to do, go to a garage, climb on the island, the pump island, and measure from the top of the island to the face of the pump, which says how many liters and all that stuff.
Mm-hmm.
Okay?
Mm-hmm.
Just go with the tape measure and measure it. Okay? Good exercise to do. Your favorite garage where you fill up with petrol. Okay? So, of course, how much light will be measured or calculated on the surfaces. So those are the things we've got to calculate. So remember, one bite at a time. Always remember that. For anything that you're doing, assignments, one bite at a time. When you're studying, one bite at a time. So when you get a question like this, think about the application. What method of calculation are you going to use? What are the dimensions of the site? They're given to you. Any other questions of your own that you need to answer? That you need to answer, not me, you, because you're doing the assignment. And what do you need to calculate? So I ask you, what calculation method are you going to use here?
The point method.
Correct. Why? Why don't you use the Lumen method?
Because the Lumen method's only for indoor applications.
And there's no box in this one. There are no walls.
Correct. Correct, yes.
And there's a floor, but there are no
Bottom.
walls. So the box doesn't exist. Okay.
Yes.
So I'm trying to help the reasoning. Okay.
Yes.
So how do you go about it? So you need to calculate what is the footprint of a single luminaire. How do you do that? Calculate the amount of light directly under the center of the luminaire. Boom. What do you do? Inverse square law. E equals intensity divided by distance squared. That luminaire, you get the data sheet for the luminaire, and you'll see it produces 10,200 lumens. So E is equal to 10,200 divided by 4.5 squared. So it's 4.5 times 4.5. Okay. And then you need to calculate what it is, not directly under the luminaire, but at the edge of its beam that it's producing on the driveway. And to do that, you'd use E is equal to intensity multiplied by cosine theta, the angle that you're dealing with, divided by distance squared, which would equal to 10,200 divided by 4.5 squared times by cosine of 30 degrees. And if you remember 30 degrees in the trig tables, the convenience table was 0.8660. Isn't that magic? Not
Magic.
because you can't see it, but I've got a head. Right. Then step 2, calculate the radius by applying Pythagoras' theorem. So you say, okay, I've got this point here, and I've got the outside point. How am I going to do it? If I had a string connecting it with a pen, I would go around like this to find out what the pool of light is going to be. Okay? So off we go. There's Pythagoras' theorem. So we say, okay, we know we've got 4.5 meters. That's the height, because they told us it's 4.5 meters. And we know the beam angles, 30, 60, 0. Although we know the beam angle is 60 degrees, all right, for the light fitting, we've got a right angle triangle, and that vertical cuts the beam angle in half. So therefore, we're only working with half of that beam angle, which is 30 degrees. You follow that?
Mm-hmm.
Yeah. If the fitting is 60 degrees, that's the whole beam angle. But we put up the vertical, all right? So we cut the beam angle in half.
Okay.
So we only use 30 degrees of it. So this bottom one is 60 degrees. Follow?
Okay.
30, 60, 90, 180 degrees. Right. So now because we've got that, and we've worked out what that is there, where that is, and we have the center point, and we measure it out to there, because we can do this on a scale. We can do it to scale on a piece of graph paper, very easy. So now we go there, and we put our compass there in your math set. Have you got a math set?
Yeah.
So you point here and the pencil there, and you go and you, there you've got it. And then you measure this, and you will find that you've calculated to 2.6 meters. So if 2.6 meters, you know, that's 4.5 meters. And you know that this is C squared is equal to A squared plus B squared. So all you do is you go and you calculate that one out, 4.5 times 4.5, 2.6 times 2.6, and it will equal a certain value. And that's once you've got that certain value, you will take the square root of whatever the value is. And when you get the square root of that, it'll be 5.2 meters. So there we've got our right angle triangle. We know what all the sides of the right angle triangle are, and that's that. And we've now worked out what the size of the circle is. So what's the next exercise? As I've said to you, I suggest you use a piece of paper and create a grid, or get graph paper. Then the grid's created for you. Scribe a circle until you've got it, and you will find there it is. Now, using the same graph paper, you now superimpose the layout. The layout. You put that onto your graph paper and you measure it out using the measurements that you're given there. Okay? It's a simple exercise which goes back to the old way that we used to do lighting design when I was a young man. Okay. Many moons ago. So we now have our graph paper and we go and measure it out. But we need to use a slight overlap. Right? Very, very slight. Do you see how small my overlaps are? Can you see them there? I've got very small overlaps. Because why? One light helps the other light. And so it goes. Okay. And once I've finished doing that, I've now got a nice map of how many light fittings I'm going to use. So now you see I've used my graph paper. I've got all those dimensions in from my layout, etc., and you can see I've actually already worked out what all the light fittings are. Okay.
How have you done those circles there now?
Because I
Sorry.
calculated, there it is. So
Okay.
if I know what that is,
Mm-hmm.
there's my entire circle.
Oh, yeah. Okay.
Right. So now I go and I draw those circles on my graph paper. There they are. I've drawn them. So if you have a look there, there's 6, 3s are 18. Okay. So I've got 18. Okay. So now we've calculated that. In our calculation, we know how much light we've got here because we calculated that using the inverse square law and the cosine with the inverse square law. So, but now what we need to do is calculate the height from the canopy underside to the pump meter height. Okay? On the driveway, we've worked it out. We're going full steam ahead. That's fine. So we've got to do that. So you've got your total height to the curb height, and then the height from the top of the curb to the pump meter face. Working in millimeters saves errors. So you've got 4.5 minus 100, because that's the curb height, minus 1240. In my exercise, I measured the pump height, minus 1240. So from the curb to the pump face, it's 1240. So it leaves me with 3.160 millimeters there, or 3.16 meters. So how do I do that? Let's go back to this one. So all that I do, because I've made the overlaps so that my pumps are also covered by the amount of light I've got, that I raise the adjacent, all right? I raise the bar up to there, which is 3.16 meters. And then I measure, I do that exercise again to see what the light is there, because that light there is going to give me my light on the pump face. All right. Very easy exercise. You must just use the methods, the tools that you've got, and it's uncomplicated. All right. So you've done the calculation already, but all you do is you do the calculation for a different height. And that height that you're doing the calculation for is the island, the pump island height, and the height to the face of the meter on the pump. So you take that away from the 4.5 and it leaves you with 3.16 of a meter. You do your calculation.
Again.
And you see what lux you got here at this point. We know what the lux is underneath the light. So we know what it will be on our driveway. And then you calculate what it is there. And that's on your pump face. And once you've done all of that, okay, there are. There's the diagram. See? I've changed it. There it is. And that's 30 degrees, remember, that I'm still working with, because the other half of that one. Okay? 30 and 30 makes 60 degrees in total. Okay? And there you've got your pump, and you've worked it all out, and off you go. And then this is calculating, which you've already done. Happiness is. And that's just showing you all that sort of thing. Distance to the pump meter. There's the height. I'm just explaining it a little bit further here for you. All right? Continuing. This is all the words, so you can read this part of it. Okay? So you can see on the pump face, we needed to have 150 lux, and we're getting 333 lux. We are sailing, plain sailing, all right, all the way. All right. I know I've flashed through those things, but I've explained it to you. It's easier to explain it as I go in those diagrams and so on. But that gives you your record for when you're looking at it again. Okay. So how do you scale a drawing? When you come to do your practical exam at the end of first year, the drawing that you get is an A4. You can print it out on your printer at home, all right? And that will be an A4. But an A4 is way less than the big drawing that the architects prepared. Okay.
Yes.
So we've got to bring that A4 to the real size, because the scale that they use is 1 to 100 in most cases. Okay. Have you got a scale rule?
No.
You need to buy a scale rule. You're not going to need it now in module 7, but in preparation for when you do it at the end of first year.
Mm.
And the scale rule will usually have different values. Now, there's my little scale rule. Now, this is very interesting because I was given this by an engineer who attended one of my workshops in Durban. Right, so we've got 1 to 1, which is, in other words, it's a ruler, 1 to 1. 1 to 100 is typically what they use on plans that we work with. Then there's 1 to 20, 1 to 200, 1 to 2,000, 1,250, 1 to 2,500, and then it's just a ruler. All right. So it's short. It's a little, probably a 6-inch ruler. All right. But it's a scale ruler. And I've had that since 2012.
Sure.
All right. So that's the scale rule. I don't use it all that much nowadays because everything is in AutoCAD and so on. So you're not using paper drawings like we used to use. Okay. So based on that, you've got to bring the A4 to the big to get the right measurements, to make sure your measurements and calculations are correct. So to do that, to arrive at the correct results, you've got to measure a known dimension using the scale rule. All right? So on the A4, there are maybe 1 or 2 dimensions that you can measure. It tells you what they are. I know on one of the drawings it's a meter, 1,000 millimeters. All right. So you work out what 1,000, if it's 1,000 millimeters on that, and you measure it, and you'll see that you'll get a certain measurement on your scale rule, but you know it's 1,000 millimeters. So then you can do a simple little calculation to work it out, etc. And this tells you how to do it. And it will be 1,900 millimeters times a factor, be 1.66. So in one of the exercises, the factor is arrives at 1.66. So you take the measurement, you write it down, and then you divide your known measurement by the measurement that you physically measured with your scale rule. All right? And that will give you your factor. And in this case, it's 1.66. So if I measured 1,900 millimeters on the drawing, and I applied the factor of 1.66, it would be 3,154 millimeters on the actual architect's drawing. All right. So there's a little process, but I'll tell you how to cope with that using Excel,
Okay.
a spreadsheet. So it does the work for you, and you keep the record there, and off you go and you do your calculations. But I teach that before the exams.
Okay.
All right. So it's a very simple process. But that you only need for the practical exam at the end of first year. All right. So let's see what we've covered. In the process, we covered in the first instance the calculation form, which you should be familiar with already in Module 7, with the yellow spaces.
Yes.
Okay. We then went through it and we looked at the light loss factors.
Yes.
And we looked at the interpolation.
Yes.
And looking at a very simple method, which is my method, which gets you to the accurate answer the same as you would do it mathematically.
Mm-hmm.
A simple answer to determine whether it's closer to one value or another value. All right. In the example, it was closer to 1 or 2. You decide whether you have to deduct from the 1 value or add and build it up from the bigger value. Okay. Then we went on, and we also looked at the limitations of the Lumen method, which we must keep in mind. Now, one of the important things that I didn't cover, and I must cover it now. If you had a space a new one. If you had a space, oops, draw. If you had a space, why is it like that? Okay, so you've got an odd shape. But in this particular instance, this was 45, and this width was 20, and this width was also 20, but this side here was 20. How would you work this out? Because you know that the length to width ratio may not exceed 1.66 to 1. All right. So let's see what our measurements are. If we take 20 times 45, I've got a calculator here. 20 times 45 is equal to 900. All right. So if I take 45 divided by the width of 20, it says it's 2.25. I can't do the Lumen method because it's exceeding 1.6 to 1. You got it?
Okay. Yeah.
2.25 is way higher than 1.6 to 1. So let me make this 48. I'm going to make that 48, all right? So if I decide I'm going to, first of all, I can't do two calculations. So I'm going to divide that into that space. And I'll say I'm going to have 48 by, no, not 48, a rubber. There it is. No, rubber. I've got to do these. I want to divide that one in two. 24 divided by 20. So I'm going to divide that in half. Okay?
Mm-hmm.
So if I take now 24 divided by 20, I'll go 1.2 to 1. All right?
Okay, now you can.
Yes. Now if I look at this one, 20 by 20 is 1 to 1, isn't it?
Mm.
It's 1 to 1. So I don't have to do anything about this one. So how many calculations must I do? So
Well,
I
the
want to
lumen method,
calculate the number of luminaires, and I'm going to do the number of luminaires for this space.
for that space.
24 by 20, all right? And I'll find out that that comes to so many luminaires. And let's call it the luminaires we're going to get for that is X. All right. And this I'll call is Y. And this one's X. And this one will be Z. So at the end of the day, if I want to know the number of luminaires, I only have to calculate that one. Because if I take that one and I double it, I'll know what that total space is. You with me? Because those two are exactly the same size. So
Yes.
I don't have to calculate that one separately. I know what it is. So I double it. And then I calculate this one. So I'll have X plus Y plus Z. And then I'll get the number. Then I'll know the total number of luminaires. So I've only got two calculations to do. I don't have to do the third one.
Yes.
Because I'll just double that to get that. So at the end of the day, this is really not a nice drawing thing. It'll be X plus Y plus Z. Okay?
Yeah.
Be equal to the number of luminaires. This thing is immensely hard to draw with, to write with it.
I can see.
But anyway, so there you have it. So you can work out for any space. But the crucial thing is always never to exceed 1.6 to 1. Okay. You got it?
Yeah.
And it's very easy. Divide the length divided by the width will give you that ratio.
Okay.
All right. Back to our presentation. So we've done that. Then you learned about the inverse square law. What is the inverse square law, Natasha? E is equal
Inverse
to?
E is equal to I divided by D squared.
Yeah. And I means?
I is the intensity.
Yes. Okay.
E is the illuminance. I is the intensity. D is the distance.
Correct. But now we want to work out the light at the edge of the beam
Yeah.
So what's the formula?
Uh,
It's the inverse square law
yeah.
multiplied
Yeah.
by cosine.
Cosine, yes.
Cosine.
Yes.
Right.
Yes, cosine. Yes.
And I want to work it out on the wall, on the pump face,
Yes.
or not on the pump face because we did that another method, but
On the wall.
on a
Vertical.
painting on the wall,
Paint on the wall.
inverse square law multiplied by
Not the tangent, cosinus, the tangent, the tan.
no, we didn't do tangent.
No, we
Sine.
didn't do tangents. Sine,
Sine.
sorry, sine. Yes,
Sine.
sine. Yes.
Yeah, I'll have to do sign language with you. All right.
Looks like
So
it.
it's not the same, not the same sign at all.
Yes.
All right. And then I took you through that whole exercise of how to do that thing. So if you get that wrong, you're going to be in trouble.
Okay.
I've told you how to do that. So you don't have to go and battle it out and say, well, how am I going to do this? I've given you the methodology. All right. So you've got those calculations. I've now taught you how to do that exercise 3. So it should be plain sailing for you.
I've got one question.
Yes, ask.
Remember, maybe you did explain it, maybe we didn't get there, but the suspended fitting.
Yes, we did it.
The suspended fitting. Yes. So if we do like the PR361.
There. Remember that drawing?
Yeah, I remember the drawing.
Can you see it?
Yes, yes, I can see it. The
Suspended ceiling. There's the fitting. Your 361's a high bay, isn't it?
The 361 is a LED high bay, yes.
Yes. So I said, here's the dotted line, which goes through the reflector. That's your reflector of your high bay. All right?
But how do we know what that height is?
Well, it depends on if you say that your room is 7 meters and the chain that you're going it's suspended to, depending on the kind of roof that you're dealing with. And usually you suspend it so that all the lights are at the same level, because you need to calculate to see that you've got the right amount of light on the working plane. Then you will know what that height is there. We can't accommodate any variances. If you know that you're going to hang that from a point there, and the chain's going to be 2 meters.
Yeah.
So then you know it's suspended at 2 meters. So you would take the height of this room space, of say 7 meters, less the floor cavity of 0.75, less this height to the center of the
There's 2
reflector
meters
of the high bay, which would be 2 meters. So you take this whole height, 7 meters, less the 2 meters, less the 0.75, and that whatever the answer is would be your room cavity ratio.
Okay, yeah, because it didn't, in the one example in the manual where it's on that PR361, that was one thing I was stuck with because I didn't know where to find that information.
The information was quite easy because you know what the dimensions of that luminaire is. You know how big the reflector is and the total height
Oh,
of
it
the
says here
luminaire?
the diameter. It gave you the diameter, the
Yeah.
weight.
And what's the height?
I don't know where
You
the
go to
height
your
is.
website.
I could
You
go
go,
to my website, yeah, but I mean, if we're looking in this
no, you won't
information,
find it on the photometric data, the height. It won't give it to you because the
okay,
height's a variable. So you
okay,
need to go to your
yeah, manufacturer's details.
manufacturer's details, and you'll go and see what is the height of your luminaire, and then depending on the design, what's the chain length. They usually give you a certain given chain length or suspension cable length, and then you can work it out from there.
Okay,
All right.
all
That's
right.
what you got to go and search for information. So if you
Yes,
know the
all right.
manufacturer, you go and look at the manufacturer's information and give it to you.
Okay,
All right.
all right.
What other questions? You got any?
I think I'm overwhelmed with information right now. I need
No,
to.
don't be overwhelmed. You just take it step at a time. Remember what I said? How do you eat an elephant? One bite at a
Yes.
time.
Yeah, so all of these angles are quite new to me, so you must just bear with me. It's like you
Yeah,
say, one bite at a time.
one bite at a time, and you've got to take it nice and easy. Don't get flustered about it, and just think about it. Just think about the
Yeah.
steps. The important thing is to follow the steps. If you follow the steps, then you can do it. Right. It's when you
Okay.
leave out steps that you find you start to confuse yourself.
I was confused the other day when I was trying to do this sheet, and I didn't know where to find all of the BF and the LRD, etc. In the meantime, all the information is right there.
It's
But I
right in
think I
front of
was
you.
so flustered. I was so flustered that I no, I don't understand this. I don't know where it is.
Yeah.
So, like you
It's
say, don't get
all there.
flustered.
It's all there.
Okie dokes.
All right. So
All right.
hopefully I can now say, like Rex Harrison said in that great show, My Fair Lady. Did you ever see My Fair Lady?
Years ago,
Years
I think
ago.
so.
Yeah. Likewise. But I remember the saying when that Cockney lady was learning to sing, the rain in Spain falls mainly on the plain. She said, the rain in Spain falls mainly on the plain. And he taught her to speak like a lady. And eventually he said, by Jove, I think she's got it.
Thank you.
All right. So
All right.
hopefully I can say that of you as well. All right. I
Thank
hope
you,
you
Phil.
enjoyed the lesson and
Thank
I
you.
hope you found it useful. Watch the video again because you'll get the link. So you can watch the
Yes.
video again, go over it, think about what you've learned, and I'm sure you will do it. All right. And
Thank you
remember
ever so
that
much.
interpolation method. That is a savior.
Yes.
All
I
right.
did copy it. Yes.
Okay. Fine,
All right.
Natasha. Thank you very
Thank you,
much.
Phil. Thank you
All right.
so much. All
Have a
right.
great weekend. We'll see you
Likewise.
later.